Welcome to this video on determining ballistic coefficient and a comparison of, I want to say, traditional G7 based solutions compared to applied ballistics custom drag models. A little bit of background. I have been shooting for 5-6 years using applied ballistics and custom drag models, and I have been extremely happy with it and have kind of regarded that as the truth. But as it turns out, I'm now considering switching to some couple of other types of projectiles, for which, at least at this point, there has not been released custom drag models. So the question becomes, will it work equally well with, I want to say, traditional calculation of solutions based on a G7 ballistic coefficient, and also I want to measure or determine by experiment the ballistic coefficient and see how it compares. So, but let's start by going to the shooting range. We're now at the range, and the idea is that we're shooting 300 meters, and we'll be positioning one chronograph here at the shooting line. I'm not completely ready yet, but that's going to be there. And then we're going to send assistant Bjarne in the trench with another chronograph, and then we are going to hopefully measure pairs of velocities, muzzle velocity and the velocity at 300 meters.
Den er på vej op.
So now we completed a session of 5 shots. They were all successfully recorded, both at the shooting line and at the in the trench at 300 meters. My initial intuition is that it seems to be pretty much what I would expect from my calculation with AB and CDM. But it remains to be seen when I get back into the office and start comparing the velocities. But I'll go down and show you what the setup looked like in the trench, and the next stop will be in the office. So here we are in the trench where Bjarne was working, and the idea was to take the target elevators, remove the boards, and then we have strapped on the second chronograph to the elevator. Something like this. And then what we did was, I was on the rifle, and Bjarne elevated or lifted up the chronograph until I could see it above the the soil or the limit towards the trench, and then he lowered it enough that I couldn't see it. And we know from previous experiments that if you're just within a meter or so from the chronograph, it'll pick up the shot. And I sent 5 shots, and it picked up all of them. So back to the office. So that was a little insight into the practical exercise of measuring velocities. I will now walk you through the results, and you can find them online. If you go to research.baso.dk, where you can find all or most of the research I've been doing. If you click on analysis, you can find an analysis called experimental determination of BC for Hornady ELDX 143 grain. So it looks something like this. And let me walk you through my findings. So I guess first I want to talk a little bit about the research question. So really it is, how does shot solution based experimentally determined ballistic coefficient BC compare with applied ballistic custom drag model for this particular projectile, Hornady ELDX 65mm 143 grain. And my SACO S20 is not as important as the 8-inch twist rate, which of course has an impact on flight. So this is sort of the question, how does traditional ballistic calculation like G7 based compare to what I've been considering up until now, at least, kind of the gold standard, the custom drag model solution. So the method, as you might have picked up from the video, I'll just quickly recap it, is to set up a set of chronographs, doppler radars, one at the firing line for measuring the muzzle velocity and one at 300 meters. So by doing that, we measure the velocities of the exact same projectile in pairs where we have velocity V0 and V300. Then I shot, and you could shoot more of course, but I decided to shoot 5 shots and record these corresponding muzzle velocities and velocities at 300 meters. And then for each of these pairs of velocities, I use a ballistic solver. In this case, I used my Gamin Tactics, which has Applied Ballistics built in, and then I key in the environment, and then I adjust the BCs until I get the observed muzzle velocity and velocity at 300 meters. So that will give me 5 G1 coefficients and 5 G7 coefficients. And then to make the result a little bit more robust, I simply just calculate the average of these BCs for G1 and for G7. Then next step is to take the calculated BCs, and of course the G7 is the more relevant one here. Then I key that into the solver using the same environment, and then I'm gonna estimate velocities and elevations, or elevation solutions I should say, for distances out to 1,000 meters. And then for the same environment and same muzzle velocity, do the same exercise but with the custom drag model. And then in order to get a sense of the differences in solutions, I'm going to calculate the absolute, I'm also going to calculate the estimated velocities and all the different distances, but more critically, the vertical difference on target for each distance for these solutions that comes out of these the G1, the G7 and the CDM solution. So that's sort of the process. And now I can show you the well, that's first the environment when this was actually done, and there's the rifle. And then, yeah, so the chronographs are 2 Gamin Xero chronographs. One C1, which is the first iteration of these, and a C2. And for the purposes of this exercise, I could perfectly fine have used 2 C1s. The new C2 has a downrange mode where it can flash when it measures a projectile. But as you might have picked up from the video from the shooting range, I actually had an assistant in the trench manually checking each shot. It was only 5 shots. So anyways, long story short, 2 Doppler radars is what's needed, or what I used. And here we have the results. So in the first column we have the shot index, so 5 shots. And for each of them there's a muzzle velocity and there's a velocity at 300 meters. And using these 2 velocities and the environment showed above, you can determine the corresponding G1 ballistic coefficient and G7 ballistic coefficient that will result in this particular V300, and that's the way to determine the ballistic coefficient. And then to make it a little bit more robust, I'm taking the average of the determined for the 5 shots for the ballistic coefficient. So I get probably the most important number would be this one. So this is my experimentally determined G7 ballistic coefficient for my particular setup. So 0.305 is the ballistic coefficient that I have found. So that's the one I'm going to use, and there's also one for G1, of course. So first thing is a table where we have different distances. We have the solution or the estimated velocities as given by the CDM, and the one from G1 and the one from G7. And I think the one thing I will note, which is kind of interesting, is that on 300 meters, which is the distance where we did a measurement, of course, by definition, 636 is what we measured. And of course, G1 and G7 gets that right, because that's exactly how I determined the ballistic coefficients. So that's not a surprise. One thing to note is that the CDM estimate of velocity is actually a little bit low, like 3-4 meters per second, lower than what's actually observed. So this could be an indication of the CDM not being exactly true. So at least for this particular distance and this velocity, it's not perfect. So okay, so maybe more interesting, let me scroll down to the next table, which consists again of these different distances in 25-meter intervals, and this is only the vertical solution, so elevation solution in millirads. So first column is the solution given by CDM, and then the solution by G1 and G7, and then the last two columns is the absolute difference in impact on target on this distance. And the solution is cited in at 100 meters. So not surprisingly, at 100 meters we have zero elevation solution for all for both CDM and G1 and G7, and of course there's no difference in the elevation. That's not a big surprise, but it's just to give you a sense of how to read the table. So in practical terms, I'm interested in when will I actually get a different solution that I would dial in on my scope. And this is in millirads. So my scope click resolution is 1/10 of millirads. So that's the equivalent of 1 centimeter on 100 meters for one click. So the way to read this, if we scroll down a little bit, oh, sorry, that was not my intention. So get this right here. So, so for example, if we look at a number like, for example, this solution, 1.29, that is 1.29 millirads. So that would be 13 clicks, because one click is 1/10 of a millirad, and so it would be, you're basically, for all practical purposes, you're just, shifting the decimal separator 1 to the right, and then you get the number of clicks. So 12.9, which is not possible, so that would be 13. Okay, so if we then walk down the list, we can see that for 500 meters, and let me just compare CDM to a G7, which is relevant. So for 500 meters, like half a kilometer, the CDM solution would be 38 clicks. And actually the G7 solution would also be 38 clicks, right? The first distance where that would be a practical difference would be at 525 meters, where I would dial in 42 clicks for CDM and 41 clicks for G7. So that tells me that at least out to half a kilometer, there's no difference. I mean, the solutions I get from the CDM and from the G7 is identical in terms of what I will actually practically do on the scope, which is kind of interesting. And then if we scroll down all the way to kind of see the extreme difference, so we're now looking at the 1 kilometer or 1,000 meter estimates. That would be 128 clicks for CDM, and it would be 124 clicks on the G7 solution. So that would give us in real world, it would mean a 40 centimeter difference at 1000 meters. This one says 43, but that's of course because I got one more decimal on the millirads, which I can't dial in on the scope. So I find that being a very modest difference, and to be honest with you, I don't know that I can say that I trust the CDM so much that I will say that a 43 centimeter difference at a kilometer would be an error. It might actually be that the G7 is more accurate. I don't know. Okay, so let me recap the findings here for you. What we've seen, it's in the beginning in the abstract. So results are as follows. The velocity estimate is actually off by the CDM by 3-4 meters per second at 300 meters. And the elevation solutions on a 0.1 millirad click scope is exactly identical for this particular projectile and solution out to half a kilometer. At 1000 meters, the absolute elevation difference on target is 43 centimeters, which, as I just mentioned, I can't really tell you which one is correct. I find that being very, very close. And then lastly, which we've not touched on, I want to mention that probably the most important number of this exercise is the G7 ballistic coefficient for this projectile, which I determined to be 0.305. I want to mention that Hornady publishes a G7 ballistic coefficient for this projectile of 0.315. So maybe not very surprising. The advertised ballistic coefficient is on the optimistic side, at least compared to what I found. So I hope you found this useful. I will say that it was actually pretty straightforward once I got into it to determine a ballistic coefficient for the projectile, and I hope it's helpful to you, and thanks for watching.